Welcome back, this is Professor Xiaoma. In this video, I will demonstrate and explain a specific hands-on problem. Now keep in mind that in demonstrating the hands-on problem, I will use an example dataset, which is default 1. When you do the homework, the dataset is different, so make sure that you adapt the code to work with the homework. In the video, I assume that whatever Python package that we will be using, you have already installed them. If you realize that you haven't installed a specific package and you need to install it in the middle of the video, simply pause the video and go ahead and install it. Install the Python package by following the tutorials that I uploaded. Now let's get started. The packages that you will need is similar to those used in recent homework assistance videos. Make sure you have the same random seed and random state. I will run this. And these two are for adjusting the style of the plots. I have created a custom function for calculating sigmoid activation. These lines will look similar to you because these codes are used in logistic regression implementation. I make a custom function to streamline the codes and make it easier to calculate sigmoid activation values. I will use two new datasets. These datasets are again the subsets of the dataset default, which you should be very familiar. This dataset is about the default outcome of customers of a financial company and their credit card department. Notice that the dataset has already been splitted into train and test. Let's do some pre-processing. As with previously, I will create an age variable and drop the year of birth because using the age variable makes more sense to analyze the problem. Let me run these codes. Note that you will need to do this for both the train and test set. Do some sanity check. Look at the columns of the train and test set. Make sure they are the same. There is an ID column, a target column, and the type of a flag variable. All the input columns match between the train and test set, so we are good. A new pre-processing step in multi-layer perceptron model is to prepare Y data to make sure that the model that you build is able to analyze problems where the target variable is a multi-label categorical variable, which means that there are potentially more than two discrete labels in the target variable. This is why we need to prepare Y data using one-hot encoding. Instead of using one-hot encoding from sklearn, we will use pandas getDummies. Why? Because sklearn's one-hot encoding is specifically designed for input data only. It's not appropriate to apply to target variables. In preparing Y data, it is critical to understand the best practices in terms of arranging the columns or labels in a one-hot encoded format. If the target variable is binary, then the rule of thumb is to arrange the smaller valued label first, followed by bigger valued labels. For instance, if the labels are no and yes, then arrange the no column first, followed by the yes column. If the target variable is a flag or integer variable with labels 0 and 1, then arrange the 0 column first and the 1 column next. Doing this will dramatically decrease the confusion and effort when you calculate the model score, for instance, the model accuracy. Let's run this. Let's do some sanity check. Here, the train set 6000 by 2 for the one-hot encoded Y data, which means 6000 rows in the training set, 2 columns, and 3000 rows in test set with 2 columns. So the 2 columns has the label 0 column first and label 1 column next. I took 3 random samples just to see how they look. To interpret the first row here, for the training example with row index 4088, it has a value 1 for label 0 and value 0 for label 1, which means this customer did not default. It has a default value or label of 0. However, for this customer with row index 589, has value 1 for label 1. That means this customer defaulted. Also, keep in mind that you should not drop any label when you use getDummies to convert the Y data. Drop first should be false. Now let's pre-process the X data. First of all, let's remove the ID and target columns, assign the rest of the columns to X data. Do this for both train and test set. Let's run this. Let's do some sanity check. Before I run the code, I would expect that the X train and Y train should have 6,000 rows. X test and Y test data should have 3,000 rows. Both Y data sets should have 2 columns. That is right. As always, let's use hypothesis testing to make sure that the 2 sets are structurally similar by examining key variables. First, test the target labels. These codes should be very familiar to you, so I won't explain them. I will simply run them. Let's see the results. So hypothesis testing returns a p-value of 1. This is the maximum p-value that you can get, which means the target label proportion across the 2 sets are similar, or you can say exactly the same. Now, t-test for equal means for all the raw numeric input variables in the data set. I have demoed these codes before, so these also should be quite familiar to you. I won't explain them, I will simply run them. Let's see the result. For a list of these columns, I get the result of the t-test, and none of these tests had a p-value below 0.05. This has confirmed that the 2 sets are structurally very similar. Proceeding forward, I will use transformer to prepare and pre-process all of the input columns in both the train and the test set. As a reminder, in using transformer, make sure you use the fit transform method to fit and transform the train data. However, you should only use the transform the test set. Do not fit to the test set. Let's run this. After running these, let's make sure that the columns of the transformed input variables conform to the expectations. Now, the expectation is that for all of the pre-processed X variables in the train set, I should see a minimum value of 0 and a maximum value of 1 across all the columns. However, it should not be the case for the input variables in the test set, because there might be random deviations in terms of the minimum and maximum number, but they should be fairly close. Here, both the X-train and X-test processed are data frame, but the columns would be simple numbers because I did not copy the column names. Let's run this. Notice that the first part is the statistics for the train set, and the second part are the statistics for the test set. Even with very short column names, the table is cut off by Jupyter Notebook because there are too many columns. This should be fine. Taking a quick look, we can see that for the train set, the minimum across all the variables are 0 from what we can see. I'm almost 100% sure that those columns that are not shown have minimum 0, and the maximum of all the columns are 1. This is the train set. That means the train set is appropriately pre-processed. For the test set, the first 7 columns, beginning from index 0 to index 6, these are the flag columns that are transformed from categorical variables, including gender, education, and marital status. For flag variables, their min and max values will always be 0 and 1. So even in the test set, they will be the same. However, beginning column index 7 all the way until the end, you would expect that the minimum as well as the maximum may not necessarily be 0 and 1 respectively, but they won't be too far. Therefore, the minimum value are almost always 0, even though some of them slightly deviate from 0. But for the maximum value, some of them are quite different, but only a few are quite different. Most of them still conform to a maximum of 1 or close to maximum of 1. Based on this analysis, I'm quite certain that the training and test set are pre-processed appropriately. Before we proceed to building a model, it's best to convert the data frames of X and Y data into NumPy arrays. Doing this will avoid unnecessary metadata mismatch, which will create a lot of trouble during the implementation process. So let's run this. Notice that dimensions conform to our expectation. Because of pre-processing, the X sets have additional columns because of the additional flag columns. I convert the data frame into NumPy arrays by using 2NumPy. This function comes handy. Let's begin to build a 3-layer multi-layer perceptron model from scratch. Notice that this model is the basic version because it uses sigmoid activation function throughout, and it didn't have the other features including minibatch, gradient descent, regularization, and the validation process. In future videos, I will demonstrate how to implement those. Here is the structure of this model that I am going to build. At a high level, this MLP model has 3 layers: an input layer, a hidden layer, and an output layer. Even though it has 3 layers, its difference from logistic regression is only the middle layer. This is the only additional layer as compared to logistic regression, so don't be too afraid of it. The input layer would be the same concept with logistic regression. I'm simply using the same symbol to represent them. As for the output layer, there was only 1 unit in logistic regression. However, here there are 2. One is to predict the label with index 0, and the other is to predict the label with index 1. As I mentioned earlier, the label 0, which means no default, has the column index 0, which this unit is trying to predict. The other unit is trying to predict the target label of 1, which means yes default. There are a lot of notations here. It may take some time to get used to, but trust me, eventually you will be familiar with this model. Some of the notations are, I will use I to denote a particular training example, J, a particular unit in the input layer. This corresponds to a particular column of the input dataset. The total number of the columns in X set is lowercase m. I use K to denote a specific unit in the hidden layer, and there are in total 7 hidden units in the hidden layer. I use L to denote the unit in the output layer. There are only 2 output units. Proceeding forward, here is other notations. I use N to denote the total number of training examples in the training set. I use M to denote the number of columns in the X train set. And by the way, I have renamed the dataset names to make it shorter so that the codes will look less clumsy. I use shorter names. TR refers to train, TS refers to test. Same thing with the Y data. I also use postfix to denote the different layers. Underscore in is the input layer, underscore H is the hidden layer, underscore out is the output layer. M, as I said, is the number of columns of the X train, which corresponds to the number of input units. D is the total number of units in the hidden layer. Here, D is 7. Based on this chart, D is 7, M is 24, T is 2. T is the total number of units in the output layer. There are several weight. W means the weight. W underscore in means the weight matrix in the input. W underscore H means the weight matrix for the hidden layer. And W underscore out means weight matrix for the output layer. Delta W, as with before, means weight update. For multi-layer perceptron model, it's better to separate the weight matrix and the bias vectors. The weight used to be weight vector, now it becomes matrix. The bias used to be a scalar, now it is a vector. So this is why it's better to keep them separate. As with before, Z would denote the net input. A is new. Previously, I used Z act to refer to activation. Now I use A to make the code simpler. E here doesn't mean the exponential expression. It refers to the error or the error propagation. Almost all of these variables have versions for the 3 layers, and the weights and biases have 2 versions, one for the hidden layer, the other is for the output layer. Here is a summary of the strategy of implementing multi-layer perceptron model inside a full for loop of an epoch. These are similar or consistent with the cheat sheet of the processes inside a for loop, here shown on the screen. To help you better understand the implementation process, also refer to the implementation timeline for multi-layer perceptron model, the basic version, as shown on the screen. With my handwritten notes, I will refer to different sections of this cheat sheet when I go through the implementation. Before we begin, we need to initialize the variables and values. A large part of this step is similar to logistic regression, but there are a few things that are different. The variable D, T are new. For now, I'm using a relatively small eta, the learning rate. Besides the cost values that need to be saved, this time let's also save the accuracy during training. Different from logistic regression, where we only need to initialize the weight vector, now we need to initialize 4. We need 2 matrices, which are the weight matrices of the hidden layer and weight matrix of the output layer, the bias vector of the hidden layer, the bias vector of the output layer, and the rest of it simply prints out all the values. Keep in mind that these weight matrices are quite big. To refresh your mind, the weight matrix of the hidden layer has dimension m by d, as is indicated on the cheat sheet. Weight matrix of the hidden layer, n by d. The bias vector of the hidden layer is 1 by d. On the cheat sheet, bias vector of the hidden layer, 1 by d. Weight matrix of the output layer, d by t. Weight matrix of the output layer, d by t. Bias vector of the output layer, 1 by t. So with these in mind, let's initialize these values and let's check the values randomly generated. So here it is. Because there are so many numbers, you can't compare everything, but simply pick a few ones on the corners and make sure that your numbers are the same as the numbers shown on the screen. Especially for this weight matrix of the output layer, it's only 7 by 2. 7 is the number of hidden units, it's D, and 2 is the T. So D by T. D by T is the weight matrix of the output layer. It's D by T. Good? Let's move on. Now I will build the complete process within for loop of an epoch. The first part of the process is the forward prop. It has 4 steps. Let's first review what are those. Here is the complete view of the cheat sheet of the implementation timeline for multi-layer perceptron model with 3 layers, the basic version. Zoom in. This is the complete view of the timeline within the for loop. Now the first part is the forward prop. It has 4 steps. The overall flow of forward prop is to first go through the hidden layer, finish 2 steps, and then proceed to the output layer, finish the other 2 steps. The first step is to calculate the net input z for the hidden layer. Now I have zoomed into the 4 steps, 1, 2, 3, and 4. The first step is to calculate the net input of the hidden layer. If you take the perspective of a single training example, take the perspective of a particular hidden unit K of the hidden layer, this would be the math that's behind the calculation of the net input. This should be very familiar to you because you have implemented the adder line as well as the several versions of the logistic regression. This is very similar to single neuron. You take the input of the previous layer, which is all of the input variables from x1 all the way to m. Keep in mind that m is the number of columns of the pre-processed input data set, multiplied by all the weights for a particular hidden unit, plus the bias term for that particular hidden unit. It's easier to use matrix notation to summarize what happens here for the entire hidden layer. Z here, it's a matrix of dimension n by d. It has n number of rows and d number of columns. It takes the input from the previous layer, which is the input layer, matrix multiply with the weight matrix of the entire hidden layer. This weight matrix has m number of rows and d number of columns, and plus a row vector here, 1 by d, which is the bias vector of the hidden layer. So by the end of the day, you get a matrix of n by d. Python implementation for this matrix notation is like this. So you'll get a matrix with dimension n by d. Now let's implement that. This cell will implement net input for the hidden layer. Just like I showed in the cheat sheet, we will use the training set as the input, dot multiply the weight matrix of the hidden layer plus the bias vector of the hidden layer. Let's run this. Sanity check. The first 2 rows and first 5 columns of this matrix, these are the numbers I get. Make sure that you can get the same number. Now let's implement activation of the hidden layer. Switch to the cheat sheet. For the activation of the hidden layer, it's simply a sigmoid activation function. It's straightforward. The dimension will remain the same. It will produce another matrix of dimension n by d. You will get a underscore h, which is the activation of the hidden layer. It has a dimension of n by d. Now let's implement that. Just like earlier I mentioned, I created a custom function here to implement sigmoid activation just so that I can save a few lines of codes when I actually implement the activation. The lines should be very familiar to you because you use them in logistic regression implementation. Since I have run earlier, I didn't have to run. This is simply to remind you. So run this. Net input has been activated by sigmoid function. Let's print a few values. Make sure you get the same values. For the third step, let's move on to the output layer, and we'll implement the net input of the output layer, Z out. The third step is explained here on the cheat sheet. If you take the perspective of a training example and a particular unit in the output layer, L means a single unit in the output layer. It could be 1 or 2 because there are only 2 units in the output layer. The net input of the output unit is a linear combination of all the input, which would be the activated value of the hidden layer. I use A to refer to the phi value of the activation function because A is simpler to look at. A can go all the way up to D because there are D number of hidden units in the hidden layer. For each of those activated value, there is a weight value for this particular output unit plus the bias term. To put it in matrix notation, capital Z of the output layer is the entire net input matrix of the output layer. It has dimension n by t, t equal 2 now. So at the end of the day, this will produce a matrix which is n by t. Capital A is the activated value from the hidden layer, which is the same thing here. It has a dimension of n by d times the weight matrix of the output layer. the weight matrix output layer has the number of rows that are the same as the number of hidden units in the hidden layer, which is D, and has the number of output units in the output layer, which is T. That's D by T. Plus the bias vector, which has dimension 1 by T. N by D times D by T becomes N by T. Plus 1 by T, it will be broadcasted to all the rows of N. You will get a matrix which is N by T. Python implementation like this, it's very similar if you compare the Python implementation of the net input between the hidden layer and the output layer. The only thing that changed are input. Earlier it's the training set, now it's the activate value of the hidden layer. And the other things that are different are the weight matrices and bias factors per se. Now it's all output layer. The dimension of the net input, the output layer, would be N by T. Let's implement that in Python. This line of code will implement the net input of the output layer, activate value as the input, dot multiply the weight matrix of the output layer plus the bias factor of the output layer. Let's run this. Print a few values of the net input of the output layer. Make sure that you get the same values. Notice that there are only 2 rows and 2 columns. How come there are only 2 columns? Because there are only 2 output units in the output layer. So even if I sliced until 5, NumPy array slice notation is robust to out-of-index slicing, so it will stop right there. You may think this could raise an error, but it doesn't, because it's robust to slicing out of bound. So this is something that's good to know. Alright, what's left in the forward prop is the output layer activation. Let's take a look at the cheat sheet. The activation here is again using sigmoid activation, which will produce a matrix that has the same dimension as the net input. The dimension will be N by T. It will remain N by T after sigmoid activation. So this should be straightforward now. In Python, here is how to implement the activation. I'm using again the sigmoid function to activate Z out. Let's run this and print a few values. Again, you'll notice that there are only 2 columns because there are only 2 output units. I only sliced the first 2 rows. Make sure that you get the same values. So far, forward prop of the first epoch has finished. Because we will use forward prop for quite a few times and the steps of the forward prop remains the same, it's convenient to make a custom function for forward prop process as long as you define it appropriately. And let's do just that. To make a forward prop function, you need to use the define keyword, and don't forget the colon here, proper indentation. A custom function has a name which should be unique. It either takes input or doesn't take any input. It conducts 4 steps and return a few parameters. Potentially, we may need all 4 results during the middle of the calculation, so we return all 4 of them just in case. Now let's examine what's inside this function. It should all be the same as the 4 steps that you just implemented. Net input of the hidden, activation of the hidden, net input of the output, and activation of the output layer. So these 4 do exactly the same. Let's run this, and the function is properly defined. It doesn't produce any output because it hasn't been called. We simply define it. But how to use this custom function? Here is how you do that. You call the function by function name, provide the train set. Here is x_tr, and I will receive the parameters. There are 4 returned objects. I only needed the activated hidden layer and the activated output layer because they will be used in the backprop process. I didn't store the net input because I wouldn't need to use it for now. Later on, you might still need them. So it's a good idea to program them so that they can be returned even though sometimes you don't need them. When you don't need a particular result, simply use an underscore, but make sure you have the index position ordered properly. Before you run this, it's always a good idea to rerun the initialization cell. So let me scroll back and rerun the initializations just in case. Make sure that the initial values are the same, the output weight matrix, and the biases. Let's run this forward prop and let's compare the values, see if they are the same as here. Run the forward prop convenient function, print out the first two rows. Now you see that the values match. So I reinitialized the values and I did one run of the forward prop.